right, welcome to part 2 of acid-base chemistry. So we have 3 parts in this chapter. Today it's going to be some calculations and talking about how to solve calculations using equilibrium scenarios. And so this is going to be kind of a repeat of chapter on equilibrium. We're just applying it to acid-base chemistry. So before we start that, let's just review our objectives for this part. So things we want to do is we kind of talked a little bit at the end of part 1 on writing KAs. So this is your equilibrium constant in terms of acid dissociation, your equilibrium constant in terms of base dissociation, and the auto-ionization of water. And we can apply that as a KW, and we're going to introduce that. And we can write all these mass actions. We can calculate pH, POH, H3O+, and hydroxide ion. And these are all interconnected. So we're going to introduce something called the K box and how you can, if you know one of these, eventually get to one of the others. Calculate the pH of weak acids and a mixture of weak acids, and then also calculate the percent ionization for weak acids. So we will do a little bit of calculation, but this is going to be primarily, I'm going to ask you to join in the synchronistic Zoom meetings where we're actually working on these problems together. Will be a large part of the objectives for this section. All right, so let's review a little bit from part 1. And remember, we had 6 strong acids, and remembering these is going to be very helpful for you. All right, so our 6 strong acids, HCl, HBr, and HI. So these are your halogens. So the only halogen that isn't a strong acid is hydrofluoric acid, and that's because the hydrogen-fluorine bond is so strong. And then we had H2SO4, sulfuric acid, nitric acid, and perchloric acid. So those are your 6 strong acids. So that means that everything else is going to be a weak acid. So weak acid is only going to partially dissociate. Some common weak acids are hydrofluoric acid, acetic acid, so this is vinegar, formic acid, sulfurous acid, carbonic acid. So sulfurous acid is not the same as sulfuric acid. So sulfurous acid has 1 less oxygen. Carbonic acid, phosphoric acid, and you see these say diprotic and triprotic. That refers to the number of ionizing hydrogens that are in that acid. And so you see here hydrofluoric, acetic, and formic acid all have 1 hydrogen that's attached to the oxygen. So it's not written this way, this hydrogen's attached to fluorine, but that's your ionizing hydrogen. When you have an acid where you have multiple ionizing hydrogens, those are going to be protic acids. And so if you have 2 ionizing hydrogens, that's a diprotic. If you have 3, that's triprotic. You can have a polyprotic, which means you have multiple ionizing hydrogens. So that means that if you look at sulfurous acid, there's going to be 2 events. One where 1 hydrogen comes off and another one where a second hydrogen comes off. So let's look at H2SO4. H2SO4 is a strong acid. This is also a polyprotic acid. Since it's 2, we can call it a diprotic acid. So there's 2 events that are happening here, and these hydrogens don't come off at the same time. One will come off and then the second one will come off. So if I look at H2SO4 as a strong acid, then that means that that first ionization event, that first hydrogen to come off, that's the strong portion. And then I'm left with HSO4 minus. I've removed one of the hydrogens. I'm left with this acid here, which is a much weaker acid. So this is 100%, this is complete dissociation. That's a strong acid. And then my second step, I'm going to take this weak acid now, and then it's going to lose a hydrogen to form SO4 2 minus. But this is a weak step, so I'm going to have an equilibrium here. So this is only partial dissociation. So this is a weak acid. This is my strong acid. So sulfuric acid is only strong in that first deprotonation event. We call that a deprotonation because I've basically removed the proton or hydrogen. The second event is a weak acid, and you're going to have this equilibrium, and the Ka you're going to have a Ka for this. If I look at something like phosphoric acid, H3PO4, this is a triprotic acid. So I have 3 ionizing hydrogens here. This is a triprotic acid. This is a weak acid from the get-go. So each of these steps is going to be a weak dissociation. So H3PO4, my first one, this is a weak acid because it's not one of my 6 strongs. H plus H2PO4. This would be my first ionizing event. Then I'm going to take H2PO4 minus, and then my second hydrogen will come off of there to form HPO4 2 minus, and then my third one will look like this. Now I have a hydrogen ion, and I just have PO4 3 minus. So these are all weak acids, so I could have 3 Kas, Ka1, Ka2, and Ka3 to denote the 3 separate events where I have a hydrogen coming off of this reaction. If I look up in a table, and a lot of these I can look up in a table, and actually in your equation quick sheet for this chapter is 4 pages, which you're probably looking at it going, oh my goodness, there's 4 pages. And so the first page is really our acid-base definitions that we did in part 1, acid strengths, which we also did in part 1, where we talked about writing this acid dissociation mass law here. And we're going to talk about ion product constant later. We're going to start these calculations today. But on the second page is a table from your textbook that has all the Ka values in a table. And so this might be handy because you're going to, when you're doing the homework, you're going to be looking up Ka values. And so you're going to be going back and forth to the book or trying to Google them. And so this just keeps everybody on the same page. I would just pull, have this handy so you can pull the Ka values here. And these are all these weak acids. And some of them, like benzoic acid, you probably never heard of before. Formic acid, you probably never heard of before. So this gives you the structure. It shows you the ionizing hydrogen in these acids and then gives you the Ka. The same thing here with some weak bases. So these are all weak bases. They're probably not things that you would think of as a weak base, like pyridine and ethyleneamine. And so this also is going to give you the KBs for those. And then the third page is this common polyprotic ionization constants. And so see here you can have sulfuric acid. You have 2 hydrogens that are coming off of this. The first one is strong. So this is going to give you the K. You're not going to find a Ka value for a strong acid because they completely disassociate. So you don't have an equilibrium scenario. But that second ionization event, this is going to be the Ka for that. So my Ka here, I would have no Ka because this is not an equilibrium, but I would have a Ka for this one, second, denoting that this is second hydrogen coming off of this of 1.2 times 10 to the minus second. So I can also find my Kas for phosphoric acid. So this would be my first Ka, my second Ka, and my third Ka as each of these hydrogens come off of the oxygens here. So these are my ionizing hydrogens. So my first one is always going to be the highest of my Kas, 7.5 times 10 to the minus 3. Then if I come down to the second one, that's 6.2 times 10 to the minus 8. And then my third one is 4.2 times 10 to the minus 13. And so that's a trend that you're always going to see with these polyprotic acids, is that the first Ka is always going to be the largest, and then it's going to get weaker and weaker and weaker. So that means that this is a stronger acid than this, than this. And if you think about what's happening here is once I've lost a hydrogen, now I have a negative charge on this species, and it's going to be harder and harder to pull off another hydrogen. And so you're going to see these Kas where you have the disassociation here into the ions are going to be smaller and smaller and smaller, indicating that these are going to be unfavored. If you look here, like this Ka is 10 to the minus 13, that tells me that very little of PO4 3 minus is ever going to be present in solution. A very small amount of that. So Ka1 is always going to be greater than Ka2, which is always going to be greater than Ka3. If you have a Ka3 scenario, you have to have 3 ionizing hydrogens to come off of here. So this one you can always bet on. The first Ka is always going to be the strongest. All right, so let's just take hydrofluoric acid and let's look at hydrofluoric acid because we've just been looking at generic ones. So let's say I have HF, and I could just write water in here if I wanted to, just to denote that there's water around. This is a weak acid, so it's going to be in equilibrium, and what's going to happen is it's going to lose, this is going to disassociate. I put water in here because this is going to allow me to denote that hydrogen ion as the hydronium ion and keep chemical reaction balanced. So I could write it this way, or I could just write HF goes to H plus F minus. They mean the same thing because in an aqueous solution, I'm not going to have H plus, I'm going to have H3O plus. So I'm going to write it this way because this is more in tune with what's actually happening in the system. My Ka for this, if I look that value up on the table, my Ka for this is 6.8 times 10 to the minus 4. That tells me that it doesn't really favor. My Ka is really small, so that means I'm favoring my undissociated acid here. If I want to write my law of mass action, let's write our law of mass action. That's going to be Ka equals my products. So we're looking at concentrations here over my reactants. And since this is a liquid, it's not going to go into my mass action. So the only things that go into my mass action are gases or things that are in the aqueous phase. So this is going to be HF. And that's going to be my law of mass action for this. The higher the Ka, the more the products are favored. The lower the Ka, the more the undissociated reactant is favored. So the greater the Ka, the stronger the acid. This Ka here implies that this is a weak acid. This is a fairly weak acid. If I look at this scenario, I can also find my conjugate acid-base pairs, if you remember from part 1. So this would be my acid, this would be my base, and then this is going to be my conjugate base, and this is going to be my conjugate acid. And my acid-base pairs, remember the definition of an acid is I can donate a proton, and so whatever picks up the proton on the reactant side is the base, and then that becomes the conjugate acid. So my conjugate acid-base pair here is HF and F minus and H2O and H3O plus. Those are my conjugate acid-base pairs. So if this is really weak, then that means that my reaction is favoring this direction here. So if my reaction is favoring this direction, then that means my conjugate base is going to be stronger. So as your acid gets weaker, the conjugate base of that acid is going to get stronger because it's favoring this direction here, meaning that it's going to pick up a hydrogen from water to reform your HF. If this is, and the same thing can be said of the converse. So let's look at a slide here. This slide just shows the relationship between acid strength and base strength. And these are acids and their conjugate base. Hydrochloric acid is going to dissociate. This is a strong acid. It's going to form chlorine as its conjugate base. This is going to be a very weak base because it's not going to reform to form HCl. So if we write HCl, the dissociation of hydrochloric acid is going to look like this, right? HCl plus, we'll write it the same way, plus water. This is a single arrow because this is a strong acid, so I'm going to form H3O plus and Cl minus. This is my acid, this is my base, this is my conjugate acid, this is my acid-base pair here, and this is my conjugate base here. The stronger this is, the weaker this is. So if this is strong, my conjugate acid is strong, my conjugate base is going to be weak. If this is weak, this is going to be stronger. Weak, stronger, stronger, weak, because I'm not going to go in reverse. For this to be a strong base, it has to pick up a hydrogen and go in this direction, and it's not going to because this is a strong acid. So you have this relationship between conjugate acid-base pairs. The stronger the acid, the weaker the conjugate base. The weaker the acid, the stronger the conjugate base. You see here, HF is kind of in the middle. All right, let's talk about water. We kind of talked about this just a little bit in part 1, where we had this auto-ionization of water. If I just have pure water, I can have this auto-ionization, and this is an equilibrium scenario where I form hydronium ion and hydroxide ion. I could just assign randomly acid-base. This is going to be my conjugate acid because it can donate a proton, and this is going to be my conjugate base because it can accept a proton. And so my conjugate acid-base pairs are this and this and this and this. This is called the auto-ionization of water because this just happens spontaneously. And I can write a law of mass action for this. So this is an equilibrium scenario, and we're going to denote it Kw, meaning this is unique to water. So the equilibrium of pure water is Kw. I told you there was lots of little subscripts here for K. So Kw, I'm going to write my law of mass action, but my law of mass action is going to omit these that are here in the reactant side because they're in the liquid phase. So the only thing that's going to go into my law of mass action are my aqueous substances, which are my ions. So my law of mass action for Kw looks like this, and water is going to fall out of it. This is also called, this whole thing is called the ion product constant for water because, well, let's just give it a really long name. Or you might see it called the dissociation constant for water, and it has a value. And it depends on the temperature, but most of the substances that we're going to be looking at are going to be happening at room temperature, which is roughly 25 degrees Celsius. Kw equals 1.0 times 10 to the minus 14. So this is a constant. I'm going to have a value for it. All of my Kas are going to be unique to the acid or unique to the base, and I can look those up in a table here. And then for water, it's going to depend upon the temperature. At 25 degrees, water is going to have this dissociation constant. And what that means, if I plug that in, so 1.0 times 10 to the minus 14 equal H3O plus and OH minus, if H3O plus equals OH minus, then these are going to be the same, and I'm going to take the square root of that. That means that each of these equals 1.0 times 10 to the minus 7 molarity. This is neutral. This is a neutral pH. Neutral water. It's going to have a pH of 7. That pH is coming from this small amount of hydronium ion that's being produced when water ionizes. If I have an acidic solution. In acidic solution, my H3O plus is going to be greater than my OH minus. I'm still probably going to have some hydroxide because just if it's in water, just from the water itself, I'm going to have a little bit of hydroxide ion in solution. But if my solution is acidic, there's going to be much more of my hydronium ion present than my hydroxide ion. In a basic solution, I have the opposite. In a basic solution, my hydroxide ion is going to be greater than my hydronium ion. That doesn't mean there isn't some of this present, it just means that there's more of this there. So as this goes down, this goes up. As this goes up, this goes down. As this goes up, this goes down. So vice versa. So let's talk about pH. Probably a good time to break from equilibrium and review pH really briefly. So pH scale. This is a unitless scale from 0 to 14, and it's a log scale. So we're going to be looking at logs. So pH, to calculate pH, I'm going to take the negative log of the hydronium ion concentration. And this is in molarity, right? That's what these brackets mean. So this is concentration in units of big M, which is moles per liter. So concentration units of molarity. Let's say my problem is I want to find my pH. So what is the pH of a solution with an H3O plus concentration equal to 1.29 times 10 to the minus third molarity? So what I'm going to do is I'm just going to plug that into this equation and take the negative log of that. So your pH is always going to be positive. So when you take the log of this, you're going to get a negative value. You're going to take the negative of a negative value. That's going to give you your pH. That's going to give me a pH then is going to be equal to 2.88941029. That's what's on my screen of my calculator. So how many decimal places do you go out? There's no default. It's not like you're just going to default to 2. You're going to look back at your original number. So it's going to depend on the number of significant figures in your original number. So in my number here, I have 1, 2, 3 significant figures. So I'm going to go out 3 decimal places. I'm not going to count this as a significant figure, because this is going to tell me how many base 10 logs I have. I have 2, and then this is where my significant figures. So if I have 3 here, I'm going to go out 1, 2, 3 decimal places. So the answer that I would report for this is pH of 2.88. 9 would be my answer. So significant figures, you're going to ignore that first number, and that's going to tell you how many decimal places you're going to go out. Let's say now I have pH and I want to calculate my hydronium ion concentration. I'm going to take 10 to the x of that. Let's say I have a pH of 1.890, and I want to know what is my hydronium ion concentration. This is always going to give me into molarities. I'm going to take 10 to the minus pH, and that's going to give me my hydronium ion concentration. So this is how I'm going to toggle back and forth. So 10 to the minus 1.890 is going to give me a hydronium ion concentration of what? And it's important that you include the negative in there. That's going to give me a hydronium ion concentration of 0.12882496 molarity. How many decimal places do I report out? How do I report this out? Because this goes to 3 decimal places, then I know I need 3 significant figures. So I'm going to write this to 3 significant figures. This is going to be 1.29 times 10 to the minus second molarity, and that's going to be my hydronium ion concentration of a solution that has this pH. And I can do the same thing with pOH. So we don't necessarily think about pOH because we don't have a scale that allows us to measure pOH, but it's the same. It's the negative log of, instead of this time hydronium ion concentration, it's hydroxide ion concentration. And this is also a unitless scale that goes from 0 to 14. So if I have a pOH, let's say I have hydronium ion concentration of 1.89 times 10 to the minus 8 molarity, my pOH of that is going to be the negative log of that. That's going to give me 7.723538196. I have 3 significant figures, so I'm going to go out 3 decimal places. I'm going to ignore that 7, and my pOH is going to be 7.724 would be my answer. If I'm given pOH, I can get to hydronium ion concentration. So let's say I have a pOH equal to 2.45, and I want to know what is my hydroxide ion concentration. So I'm just going to take 10 to the minus pOH is going to give me OH minus. So 10 to the minus 2.45 is going to give me that hydroxide ion concentration. And that is 0.0035484134. And now I'm going to look at, this has 2 decimal places, so I'm going to go out 2 significant figures here. So my OH concentration would be 3.5 times 10 to the minus 3 molarity. Now, the nice relationship that you might want to keep in the back of your mind is if you take pOH and you add it to pH, you're going to get 14. So if I have my pOH and I want to know what my pH is, I don't have to go through trying to do this calculation. I can just subtract from 14. So pH equals 14 minus pOH, and pOH equals 14 minus pH. So that's a handy little conversion to have. And here is my pH scale. So here you can see pH and hydronium ion concentration are related. So the higher my hydronium ion concentration, meaning this direction, the more acidic it is. The smaller my hydronium ion concentration, now I'm in 10 to the minus 14, the more basic it is. Now there's this thing called the K-box, and the K-box is going to relate everything together. And that looks like this. Okay, so this is called the K-box. And I'm going to put hydronium ion concentration up here in this corner and pH here in this corner, and I can relate these together. So I can relate this to this by taking pH equals the negative log of hydronium ion concentration. So if I'm given this, I can get to here. I can also go in reverse. If I'm given pH, I can get to hydronium ion concentration because I know that H3O plus equals 10 to the minus pH. So I can toggle back and forth that way. I can also do the same thing with hydroxide and pOH. So I can go this direction here, and my pOH equals the negative log of OH minus. I can go in this direction, and my hydroxide ion concentration is equal to 10 to the minus pOH. Now I also know that I can go back and forth this way. So I can go from pOH to pH because pH equals 14 minus pOH, and I can go from pH to pOH because pOH equals 14 minus pH. So I can do that. And lastly, I can convert between these because I have this auto ionization constant for water. and kW, remember, is 1.0 times 10 to the minus 14. So this allows me to toggle between these two as well. So if I want to go from OH to H3O plus, OH is equal to kW divided by the hydronium ion concentration. So I can go that way. And I can also go this way, where my H3O plus is equal to kW divided by OH minus. I can use this K box to go any way I want to. The thing I can't do is I can't go directly here, and I can't go directly here. This is not going to happen. So if I'm here at POH and I want to know hydronium ion concentration, I either have to go here and then here, or I have to go here and then here, but I can't go directly. So there's no direct route around this box. There's no shortcut through here. So I'm either going to go from POH to HOO, hydroxide ion concentration, to H3O concentration, or I'm going to go to pH to hydronium ion concentration. So those are my choices. So first is figuring out where you are in the box, and then which direction you want to go to get to where you're going. Stop here for part 2A, and then we'll pick back up with part 2B in a bit. And I don't know what's happening with this video. When it was recorded, there's a lot of like staticky stuff in here, so I apologize for that.